the first and opening session of the meeting.
Thank you, Maria. Hello, everyone. Hello to our remote participants. It's a great pleasure to open the scientific program and welcome our first speaker, who is Tatjana Galatyuk from Darmstadt. And she will tell us about decoding the phase structure of QCD at large chemical potential. So we start with reality, with an experiment. And Tatjana, I will tell you in the mic when you have 10 minutes left. Okay.
Okay,
please,
good,
ahead.
great, thanks. Yeah, good afternoon to everyone, and thanks over for introduction, and also to the organizers, Maria Paula, thanks a lot for the opportunity to speak at this workshop and to tell you a little bit about how we would like to understand the phase structure of the QCD phase diagram at the high baryon chemical potential from the experimental point of view. And I will also focus on the specific observable to characterize this particular place on the QCD phase diagram. So just to set the stage, and we will see this during the week many times, I also would like to start from the QCD phase diagram, which we summarize usually as a function of temperature and baryon chemical potential. And what we can say now about this QCD phase diagram is that we do have an excellent guidance from the lattice QCD calculation at the finite chemical potential. And at this vanishing chemical potential, what we know from the lattice QCD calculation is that the pseudo-critical temperature for the physical quark masses is situated somewhere at the temperatures of 156 MeV, which is meanwhile is also known with the high precision. And what we also know from the recent papers to which I'm referring to is that in the chiral limit, if one try to also estimate where the position of the possible critical endpoint, it is now as low as 98 MeV, which of course also attracts quite substantial interest from the experiment and also from the effective theories which are inspired by the lattice QCD to predict the phase structure at the high chemical potentials. So what we know from the lattice QCD inspired theories is that indeed critical point might exist. And how do we know that? Because one predicts the first order deconfinement phase transition. And by having this deconfinement phase transition on the one side and the crossover as predicted by the lattice QCD on the other side, they must meet somewhere in the critical endpoint. So we still do not know from the neither theory nor experimental side where exactly this deconfinement and chiral phase transition are taking place, where the limits of the hadron existence at which exactly temperatures and densities we start to see matter which is called quark-gluon plasma. And also what we would like to do is to characterize these different states of matter by means of the equation of state. So I think we all know that there are quite large discovery potential related to this high MeV region. And it is not like this, that this region of the QCD phase diagram was not studied experimentally before. So in general, the experimental challenge, of course, is to locate this onset of deconfinement and critical endpoint, but also to understand microscopic properties of matter at various temperatures and also various baryon chemical potential. So what you see here is now again the same QCD phase diagram, which is plotted together with the experimentally obtained data points. Those are chemical freeze-out values of temperature and baryon chemical potentials, which are extracted by means of comparison of statistical hadronization model to the hadron yields as measured in experiments. And you see that these data points are densely populating this QCD phase diagram. But when it comes to the rare probes, like for example, electromagnetic probes, there are only two distinct measurements, which we also try to put on this QCD phase diagram. And this is all about the future explorations from the experimental point of view to map with the rare and penetrating probes different regions on this QCD phase diagram. So what we use experimentally are the production of the particles. They could be from the light to the strange to the charm, particles containing charm quarks. We also look to the event-by-event correlations and fluctuations. In this way, we can also study criticality on this QCD phase diagram. And then last but not least, to really understand the emissivity of the matter, we use dileptons. And as I pointed out, by means of charm, event-by-event fluctuations, and dileptons, this QCD phase diagram is not addressed in the most of the regions of the temperature and chemical potentials. So one way may ask why it happens so, and here I try to sketch you all what we did in the recent decades and years, and indeed in the dash for the new machines and ever highest energies, we made the rapid step with respect of the collision energies from Beverlag to AGS, SPX, RHIC, and LHC. But by doing that, there are many questions which are left unanswered and related to the small center of mass energies. And the interest to this particular range of the center of mass energies, which is also translated to the high baryon chemical potential, has been changed dramatically in the recent years. And I think Claudia also in her talk will address all the activities related to the beam energy scan at RHIC with the star fixed target experiment and also in the collider mode. We do have a long program also at energies of GSI, which is in Darmstadt, Germany, and there are many new experiments and facilities that are being planned and will be built to study this QCD phase diagram. So as I mentioned, there are many observables, but I will focus in this talk today on the observable which I think is the most promising to address phase transition and possible existence of the critical endpoint. And this observable is electromagnetic probes. So here, just to give you a rough idea, where do we stand right now with the experimental results from with respect of the electromagnetic probes. Here's this little sketch which shows existing ELIS and existing STAR experiment, former Phoenix, Ceres, and NA60 experiments, which study phase structure at high energies or well, small baryon chemical potentials. And on the other side, if you look to the high chemical potentials but moderate temperature, there is only one experiment which was and still running with the name HADES, high acceptance dielectron spectrometer. And in the range where first order phase transition and critical point are predicted, there are no experimental facilities and also experiments that can address this range of the QCD phase diagram with the rare probe. And I will address this point also at the very end of the presentation. So what we try to do, we try to use experimental results from the existing experiment and to see how useful is this electromagnetic probes to study the QCD phase structure. And to convince you that this is an ideal probe, let me start from the very beginning and from the basics, and then I will discuss several observables in context of the and relation to the QCD phase structure. Electromagnetic probes, as you all well know, they produce through the entire collision of the two heavy ions. They are not subject of the strong interaction, therefore they carry to the experimental setups information about the matter at which they have been produced. And by this, we could also study properties of matter at different temperatures and different chemical potentials. In fact, what we learn and what we establish meanwhile is that by measuring dileptons in experiment, we can use them as spectrometer, chronometer, barometer, thermometer, polarimeter, and amperemeter of this heavy ion reaction at different collision energies. What do we do in experiment? We study so-called invariant mass distribution of either electron positron or mu plus, mu minus. Here you see the simulated spectra, which has very characteristic features. For the dileptons which decay into electron and positron, we have at the very small masses sources which are contributing to the spectra from the so-called decays of the long-lived mesons like pi 0, eta, but also omega phi. This is also clear that depending on the collision energies, different sources of the electrons and positrons could contribute to the spectra. And if energy is high enough, then we also have contribution from electron and positron from the so-called correlated d and d bar decays. Also, Drellian contribution is the part of the spectrum. And these sources, which I mentioned just now, they are not of the big interest, because what we are particularly interested in experiment is to access so-called thermal radiation from the QGP and also from the hot and dense hadronic medium. So these sources are indicated here with the red curve. And this is to what I will refer in the coming slides as excess yield, which is equivalent to the dilepton yield after subtraction of the long-lived, so electron positrons from the decays of the particles at the freeze out, but also when one takes proper care about the contribution of electrons and positrons from the so-called first chance collisions. In order to calculate electromagnetic production rate, one starts from the current correlation function, and from there one could extract rates for both, for real photons and also for dileptons, just as they presented here. So imaginary part of this current correlation function is called photon self-energy, and it also, in case of the photons, directly describes the transverse momentum distribution of the particles. And here comes the very big and important difference between the real photons and dileptons. Dileptons, they do carry a very important additional information, namely invariant mass, which means that if you measure in experiment invariant mass distribution, you do have a direct access to the in-medium spectral function. So this is beautiful because, as we will see also later on, in terms of the determination of the temperature of the source, for example, this makes a very big and distinct difference between the photons, real and virtual one. So this electromagnetic correlator is well known in the vacuum, as we also can see in the particle data booklet. In the low mass region, so below 1 GeV, this spectral function is saturated by the light vector mesons like rho, omega, and phi, given the raised to the vector meson dominance due to the fact that spin and parity of the virtual photon and vector mesons are identical. And here you can see also this rho omega phi with the distinct peaks at the small invariant mass ranges. So now for the large invariant masses, like above 1.2, 1.5 GeV, one do not see any longer any peaks on this distribution, and dileptons are mainly defined by the perturbative QCD continuum, like the quark, anti-quark annihilation and hadronization. What is also important to mention in this figure is this dip, characteristic dip between 1 and 1.2 GeV, and this would be also of interest for the further discussion because we can use this range in the spectrum to monitor the behavior of vector, axial vector in the medium. So how do we do that? Before we go to the medium, we have to constrain our spectral function in the vacuum for vector, axial vector. So we know that in the vacuum, chiral symmetry is being broken because of the non-vanishing value of the quark-antiquark pairs. So condensate here is shown as a function of temperature. And we know from the lattice QCD calculation that when you change the temperature, you also change the quark condensate, and this is shown here with the dots. There is a beautiful relation between this quark condensate, and also difference between the vector and axial vector spectral function, which is provided by the QCD and chiral sum rules. So here you see this difference between vector, axial vector, and also QQ bar. So what we know is that this QCD and chiral sum rules, they are accurately satisfied in the vacuum, as we also know from the data and description of the data from the Aleph. We also know from the calculation of 90s that the QCD and chiral sum rules, they remain valid in the medium. So therefore, this relation between the in-medium spectral function of vector, axial vector to the chiral condensate really provides us a very good possibility to understand the study, the onset of this chiral symmetry restoration by means of the vector and axial vector correlators. What does model predict for the behavior of this vector and axial vector spectral function in the medium? Here you see the calculation for the chemical potential of equal 0, but with the baryons and antibaryons being included in the model, and for different temperatures, starting from 0 and then towards the higher temperature. The characteristic feature that we can see here is that the raw meson melts without being shifted towards higher or smaller masses, while the chiral partner of the vector meson, so axial vector meson A1, moves towards the smaller masses, and then it degenerates with its ground state, as shown here for the case of 170 MeV. Very similar observations are also done by the functional renormalization group, where one can also calculate the quark condensate behavior as a function of temperature. Here one can see that there is a very nice agreement between this calculation and also lattice QCD calculation. And what is very beautiful is that within the same framework, you can also calculate the spectral function of the vector and axial vector particle, which you see in the lower panel. The dashed curve is again A1, the blue curve is the raw particle, and here you can nicely see that when temperature is increasing, both particles become degenerate, and also confirming what we have seen from the Yang-Mills model, that raw particle stays practically unchanged with respect to its mass, while the chiral partner approaches its ground state and then degenerate at the high temperature. What is also important to mention at this moment is that this is also valid not only for the mesons, but also for baryons. And this we know from the lattice QCD calculations, where they try to calculate nucleon and also chiral partner of the nucleon, which is N star 1535. What they have seen is that at the high temperatures, like parity doublets are appearing. And also here, there is the very characteristic feature that for the nucleon, independently on the temperature of the system, mass of the nucleon is found to be independent of the hadronic medium, while its chiral partner N star 1535 moves towards the ground state, so mass of the nucleon and at high temperature becomes identical. So this happens at T over Tc of 1.9. So these effects one also has to take into account when one speaks and discuss the medium modification of dileptons. So now, having these constraints from the lattice QCD calculation, one can also ask the question, at which moment can we speak about matter going from the hadronic phase to the quark-gluon plasma phase? And this one can try to do by changing again the temperature of the medium, and then to see at which temperature in medium spectral function would match the rates as calculated from the lattice QCD. And what one can see also here is that the higher the temperature, the more and more closer in medium spectral function and also rates calculated from QCD, magenta dashed curve and the red curve is being practically identical at these temperatures of 180 MeV. And here, of course, is the question, if we see this degeneracy between the spectral functions calculated in the lattice QCD and from the model calculation, if we could say this states that there is an evidence of the transition from the hadronic to the quark-gluon plasma phase. Now I move on with the spectral function which found to be most successful in the description of the experimental data, as I will show you in a second. This is many-body theory. It uses effective Lagrangians to model different contributions to the raw meson self-energy in the medium, as indicated here. So you see there are additional terms because of the interaction of the raw with the pions from the thermal bus, but also due to the direct coupling of the raw meson to the baryons or mesons. And what this model calculation predicts is that we do see a quite substantial melting of the raw meson when we start to increase the temperature. But what is particularly important is that shape and also how much of the raw survives in the spectra depends a lot on the density. And here you can see when density is around 4 times of the normal nuclear matter density, one observes a very strong broadening of the raw meson. And just to mention that baryonic effects are absolutely crucial for that. So how to test this in experiment? Let me start from dileptons as spectrometer. And here I show you exactly the proof of the fact that baryonic effects are absolutely important. And I use here example from the CERES measurements of the lead-lead collisions of at square root of 7 GeV in the center of mass energy, and also an A60 measurements for the dimuons, together with the model calculation, many-body theory, as I discussed just now. And you can see that both data sets, so CERES data, still have substantial statistical systematic errors. One sees already, again, the distinct difference between the curves with and without baryons being included in the model. And with the precision data of an A60, one could really understand and see this effect of a full model and also model when the baryon coupling of the raw to the baryonic resonances were excluded from the model. And here you see the big difference between the model and the data in case these baryons are not taken into account. So how does the situation changes if we move with the energy towards higher energies? So we go now from SPS to RHIC and also LHC. So here we have measurements from the STAR, Phoenix, and also ALICE collaboration. STAR also managed to extract this excess yield, acceptance corrected. Phoenix data together with the cocktail, but it also includes the calculations from the many-body theory, and same true for the ALICE experimental data. So more events and better statistics is still needed for the LHC energies. So nonetheless, the conclusion is like this, that this model calculation describes experimental data very well from SPS up to the LHC energies. And this also indicates how important to include the effects of the baryons and antibaryons even at the chemical potential of equal 0, because coupling of the rho to the baryons and antibaryons is independent whether the chemical potential is equal 0 or it's distinct from the 0. So now, since the model works so well for the high collision energies where we still have system which is pion dominated, the question of course comes how to compare this successful spectral function to the collision energies at which baryons are dominated system. So here the situation is less evident and more complicated. So one has to first of all establish which part of the fireball has been in the thermal equilibrium, because that's for what the spectral function is being calculated. However, there is the very beautiful framework provided by combination of the microscopic transport model, which are beautifully describing the bulk observables, together with the rates calculated in the local equilibrium, which also demonstrates to work nicely for the wide range of the collision energies. So this method called coarse-grained approach, where one tries to establish temperature, density, chemical potentials, expansion velocity of the system by means of the transport model calculation. And then one used the in-medium spectral function to calculate electromagnetic emission rate. And by doing that, one could compare this to the experimental results at the lower collision energies. This comparison I show you here. On the left-hand side, you see measurement from the Hades collaboration for collision energies of just 2 GeV per nucleon. And this data are again compared with the spectral function, which successfully described dileptons from SPS up to LHC energies. And also here you can find data in the nice comparison to the model calculation. So with this, one could say that we do have a tool and also a way to model the spectral function along on the wide range of the temperatures and chemical potentials. So what we can do with this as next, we can try to see if this model also equally well works for different collision systems and also for slightly different energies. And for that, we have collected also set of the data on somewhat lighter system, but again, two complementary energies to the measurements I showed you before. And what you can see on the right-hand side is also results which show the behavior of the excess yield as a function of participants, but also temperature of the fireball extracted for two different collision systems. And result seems to be consistent, and we have to now see how well they are compared to this model calculations. Now one can also ask the question, which process is really responsible for the system thermalization at this low collision energies? And one of the possibilities is related to the fact on how we view the nucleon. So we know there are quite some discussions already in the past about nucleon as the quark core and also surrounded by the meson cloud, pion or kaon. And what one still have to prove from the experimental point of view is how exactly the photon couples to this nucleon. And this what one can do by studying electron-positron production in the pion-induced reaction, where one could really try to understand how does the nucleon look like. And here you can see measurements with the black dots together with many model calculation, but please focus only on the red curve, which is plotted together with experimental data. This model includes both quark core and meson cloud, and this model is the one which describes our experimental data best. So this is the first conclusion, that this meson cloud playing an important role in this physics. And another important point from these measurements is that in the process of the raw coupling to the nucleon, the N-star 1520 playing a dominant role. And the process is ongoing via vector meson dominance. And as I showed you at the very beginning on the slides, this vector meson dominance model is the basis for the emissivity calculation of the QCD matter for different energy regimes. So what does it mean, and what can we conclude? We can conclude is that this meson cloud is playing an important role and guide or lead the system to be internalized in these low collision energies. And this has been nicely described in this paper from Fukushima, Koyo Weise in 2020, who describe the matter at 2 times of the normal nuclear matter density as the matter which is in the so-called soft deconfinement. What is meant here is the following: if you view nucleon as the quark core and meson cloud, and you start to compress matter to the high densities, the first part which come in the contact with each other would be a pion from the cloud of the nucleons. And in this way, one can just see that also the quarks from the quark cores could more freely roam in the system which is compressed to the higher collision energy. So I think this also combination with our measurements in the pion-induced reactions makes a very nice view on how the system at high density could look like. So dileptons as a thermometer, how do we do that? From the rates, we can try to connect the rates measured in the experiment to the so-called Planck-like radiation. Important to mention here again is that invariant mass distribution is not affected by the flow, and therefore the measurement of the temperature could be done in the direct way. And so this temperature is an average one because dileptons are radiated from the early but also from the later stages of the heavy ion reaction. Even this average temperature at SPS energies has been extracted to be 205 MeV, which is roughly 50 MeV higher than the one from the chemical freeze-out temperature. Also pointing to the fact that we do see in our dilepton spectrum contribution from the QGP, otherwise temperature would be not as high. And in fact, one can also say that this is one of the first explicit temperature measurement above the pseudocritical temperature in the heavy ion reactions. How can we use this temperature? This temperature has been extracted, as I mentioned, just by 2 experiments, Na60 and also HADES, and these measurements are plotted here with the closed red symbols, square for HADES, circle for Na60. We can use now measurement of this temperature as a function of square root S in order to see what happened in case system is at the phase transition, or if we probably have a crossover all over the places. So these open symbols are these particular calculations when we do not assume any phase transition, and you see the smooth falling of these temperatures from the high temperatures to the low temperatures. And the question here would be, can we see the signatures of the first order phase transition which could be reflected or seen in the plateau of the temperature in this diagram of T versus center of mass energy? Just to visualize this even more, we do have guidance from how this temperature or similar temperature as a function of energy could look like from the measurements of the nuclear liquid gas phase transition. And here you see this characteristic plateau in this temperature behavior And if we will be able to measure this with the dileptons, that would be quite a nice evidence for the phase transition in the heavy ion reactions. Another signature of the phase transition, or even better to say, to characterize which kind of this phase transition it was, one could also study behavior of the dileptons at the masses above 1 GeV. And here, as I mentioned also to you at the beginning, for the vacuum spectral function of the rho and A1 of the vector, because axial vector is not measured in E plus E minus, there is this characteristic dip at around 1.2 GeV. And already long time back, 1990s and 2000, there were predictions on what will happen if one puts the rho and A1 in the medium, and the effect of which has been discussed is related to the rho A1 chiral mixing. How one can see this rho A1 chiral mixing in the experiment is indicated here. You see that in the mass above 1 GeV, one would see like the feeling of this dip by the additional electron positron or mu plus mu minus yield, which is as high as about 30%. And with the high precision data, we should be able to measure this. Of course, there are challenges to do that. And here I show you example of dilepton spectra at 20 GeV. This is roughly 7 GeV root S, and also for the Alice energies at LHC, so LHC tera electron volt per pair of nucleons, to really monitor invariant mass distribution at 1 GeV, 1.2 GeV invariant mass. We have to take particular care about contribution from the Drellian at the lower collision energies, while the DD bar contribution is quite suppressed at this particular collision energies. If we now move on to the LHC energies, the contributions get somewhat different, but still by having negligible Drellian contribution, one starts to have really overwhelming amount of electrons and positrons from the semi-correlated CC bar, BB bar contribution, but also from the QGP contribution, which one has to take into account when one would like to extract the signal of the rho A1 mixing. And here we speak of the hadronic matter at high temperatures, high densities.
You have about 10 minutes left.
Yeah, thank you. But there is no mission impossible, and experiments, future experiments, they do show that there is the chance to measure this effect. And here I show you simulation from the NA60 Plus and also Alice collaboration for the future measurements of the dileptons. Dileptons as ampere meter. Here we try to relate spectral function of the E plus E minus to the electrical conductivity, because it has been shown already in 2006 by Guy Moore and collaborators that in the limit of very low mass and very low transverse momenta, there is a transport peak by measuring which one could directly access the electrical conductivity. So also from the recent calculation from the many-body theory, one demonstrates what happens to this transport peak if one put spectral functions and in different temperatures, but also when one includes the thermal pions into the medium. And what is seen on the spectra is that transport peak broadens substantially. So the idea would be to measure with precision spectral function and towards very low mass and very low PT in order to extract this electrical conductivity. This is something for future, but still let me give you some views on that. Here on the left-hand side, you see already existing experimental data from HADES in the plane of transverse momentum and invariant mass distribution. And you see that with these HADES measurements, we can cover PT and mass towards practically zero, which could be essential in discussing this electrical conductivity. Here also just example of the invariant mass distribution for the small momenta. For the new experiment at LE3, there also tries to access this region of the small mass and small PT, but there will be approximations needed in order to extract this electrical conductivity. Still, by having these measurements from highest, lowest energies and also in between, we will be able to map this electrical conductivity as a function of temperature. And here you see currently quite large spread in the literature, and it would be nice to contribute here also from the experimental point of view. Last 7 minutes of the presentation I will spend on discussing dileptons as chronometer. For that we use dileptons or excess yield measured in experiment. There are two ways of extracting lifetime of the fireball. One is shown on the left-hand side together with an A60 data model calculation, assuming different lifetime of the interacting fireball, and this lifetime could be extracted with the precision of 1 femtometer. Another possibility of measuring lifetime of the system is to integrate dilepton yield in the mass range between 300 and 700 MeV and check how this excess yield behaves as the function of collision energy. So this has been done now in several experiments. Precision is not yet sufficiently good, but what we can see from the model calculations is that lifetime and also integrated yield of the dileptons coincide. Therefore, by measuring this yield in this particular mass bin, one can nicely establish the curve for the lifetime of the interacting fireball. So why it is so interesting when we speak of the phase transitions? Because if we have a first phase transition or critical point, system would need to go via this phase transition. This is, as we know from the evaporation of the water related to the latent heat, if system lives longer, it also radiates more dileptons, and by seeing some deviations from the quite a constant behavior of this observable as a function of collision energy, one should be able to also see phase transition or even existence of the critical point. And this has been tried by model calculations. So here you can see results from the functional renormalization group that try to establish difference between the dilepton rates when one calculates them close to the end point, but in this time it has been calculated for the nuclear liquid case phase transition. And here one can see that effect of this phase transition and critical point is reflected in the yield of the dileptons. One observes up to factor of 3 more dileptons in the spectrum. What has been also tried is to calculate the same observable, so extra yields of the dileptons, implementing the first order phase transition into the hydrodynamics. And also here one observes factor of 2 more dileptons in the spectrum, and this factor 2 should be easy to observe in the experiment. So what we learn from the dilepton spectra is that we do have system which radiates dileptons during the substantial lifetimes of approximately 13 femtometer, that these photons are radiated from the system which is in thermal equilibrium, Temperature of the system is 70 MeV and density of the order of 2 to 3 times of the normal nuclear matter density. And all these observables provide a fantastic opportunity to connect another extreme, which has been recently observed in both gravitational and also electromagnetic spectrum of the binary neutron star merger event, as shown here. On the left-hand side, you see distribution of the temperature and density for the neutron star merger event and also for the heavy ion collisions at 2 different collision energies. And if one looks here at the collision energies of 600 MeV, one sees that the temperatures and density probed in this heavy ion reaction are quite comparable to what is seen in the binary neutron star merger event. With even further steps towards producing and using same equation of state to model both neutron star merger events and heavy ion reaction, I can only refer to this recent paper in which it very clearly shown that if you use self-consistent relativistic hydrodynamic calculation for both neutron star merger events and heavy ion collisions, system indeed goes through the similar temperatures, densities, and also has very similar entropy per baryon values if one looks at these energies below 1 GeV. Yes, and of course one would like to understand which type of the matter is being produced either in heavy ion reaction or in the binary neutron star merger event. And here also very recent view on how can we really characterize and see mechanism for chiral symmetry restoration in the dense nuclear matter, which is relevant for these neutron star merger events and small collision energies. So here parity doublet model has been used. In this parity doublet model, one sees properly nuclear liquid gas transition, but also the chiral phase transition appearing on the temperature chemical potential plane. And by using this parity doublet model, one can also calculate how does the vector and axial vector spectral function behave close to the critical endpoint. And this is now chiral critical endpoint. So you see also here characteristic features we discussed before. Spectral function become identical at close to the critical point with the very characteristic peak at frequencies of around 300 MeV, which is an effect of the rho plus n going to n star 1535 process. And this peak is then directly seen in the DILEPTON spectrum, which we now try to extract in terms of using the spectral function and doing the full coarse-grained as discussed before. So this is the future, and this is where we stand now and work towards the future with many other experiments, as I discussed already before. Future is bright, many new experimental facilities that would like to address this regime of nuclear liquid phase transition, chiral phase transition, and also we do have a new frameworks in the theory to consistently describe equation of state and spectral functions of the vector and axial vector particle. With this, I finish, and I probably don't need to read these conclusions. I think we do have quite a good way of searching for the deconfinement and chiral phase transition by means of dileptons. But of course, there are many other observables which one can use to study, for example, equation of state. But all these observables are statistics hungry observables. Therefore, new facilities are absolutely essential to address this very interesting range on the QCD phase diagram. And with this, I would like to thank you for listening and happy to take questions.
Thank you very much, Tatjana, for this great overview over your experimental efforts. So we can take questions from here as well as online. If you raise your hand, I see one question online from Chihiro, please.
Hello. Hi, Tatjana.
Hi.
I have a comment on your statement about 30% more yields because of raw A1 mixing. You should be careful with the extrapolation of this mixing theorem to higher temperature, because especially near the chiral crossover, this theorem is not valid because it's just inconsistent to degenerate raw and A1 states. So I'm afraid that the 30% more yields is presumably overestimate.
Yeah, thanks indeed, Chihiro. This I should have mentioned. So this 30% yield in the spectrum, one would see with the, first of all, full mixing of rho and A1, which probably also not the case, right?
Right, because of finite pion mass. Mm.
Exactly, and then this factor, which you say, yes, yeah. So it's challenging measurement. Even, you know, the 30% for experimentalists would be a challenging already, absolutely.
Mm.
Okay, then we have a question here.
Tatjana, you hear me now with the micro?
Yes,
Okay.
yes, yes.
So thank you very much for this nice talk. I just want to mention and make a comment about this hardest data. I mean, we developed transport theories now since 2 decades in order to study the GSI energies with transport approaches. After the really thermal transport approaches have completely failed about 20 years ago, Walter Greiner did a lot of these things. But at the end of the day, it turned out it's a non-equilibrium process with a lot of facets, with a lot of things which have been checked, from the strangeness up to the dileptons and from the basically proton up to the pions. So I think it's a little bit courageous to say that now from the hardest data, one can really make conclusions to the big size system like neutron star mergers. I think the non-equilibrium aspects, that is 2 GeV or 3 GeV data, are that important that it's really very complicated to extrapolate from heavy ion collisions now to these big systems, which are really characterized by a temperature and a chemical potential.
Okay, so I don't know to comment on this. So maybe I will go back and refer to these dileptons. I fully agree, in particular, if we speak of hadronic phases, hadronic observables. But what we do know from the dilepton measurements is that starting from roughly 7 femtometer, this is this middle plot which I show you here. And 7 femtometer, you need for 2 nuclei to overlap with each other. But then from 7 femtometer on, indeed, one at least sees that system seems to be in the equilibrium. So this, in general, what lead us to use this coarse-grained way of interpreting dilepton spectra using spectral functions and rates calculated in thermal equilibrium. So
okay,
yeah,
I'm afraid we should move on and continue the discussion later on. I don't know, maybe you can connect, or meet. Thank you very much, Tatjana, once again. Thank you also for the question.